Let's take a look at problem 3. It says you gently place an 800-gram block on a vertical spring. The spring compresses a distance of 5 centimeters and the block is at rest. Next, you remove the block and drop it from 1.2 meters above the spring. The spring compresses and then shoots back up into the air. We have two questions. A, calculate the spring constant, K, of the spring, and B, calculate the maximum compression of the spring. So first, let's draw a picture, or let's take a look at what's happening in this problem. Here are diagrams representing the situations described in the problem. Diagram 1 is a picture of just the spring at its initial length. Diagram 2 is after the block is placed on it and it's allowed to lower slowly to its equilibrium position. Diagram 3 is when the block is 1.2 meters above the spring, so the spring is at its equilibrium position and the block is dropped or released from rest. Diagram 4 is just before the block hits the spring, so it has some speed going down. And then diagram 5 is where the block has hit the spring and compressed it to its maximum point, and in a moment after this, the block will then shoot back up into the air. In situation 2, the speed of the block is 0, but also the acceleration is 0, because not only is it not moving, it's not accelerating. So it stays not moving. It has a constant speed of 0. Whereas in diagram 5, its speed is 0, but its acceleration is not 0. It has come down, it's at the bottom of its travel, but it's going back up in a moment. It is still accelerating, it is still changing its velocity. So let's answer these questions. Part A, calculate the spring constant of the spring. So what I'm going to look at is situation 1 and situation 2. Situation 1 shows the initial or the equilibrium length of the spring, the equilibrium position. When I place the block on the spring compresses a distance d2. And so if I draw a free body diagram of the block in this position, I have forces of gravity and the normal force from the spring, I'm just going to call it F sub s. And that's all I have. So we have, and again this equals 0 because the acceleration is 0 in case 2. So the spring constant is 156.8 newtons per meter. Now let's try to calculate part B, the maximum compression of the spring. So for part B, I'm going to look at situations 3, 4, and 5. And this type of problem is an energy conservation problem. Because there's no non-conservative forces in the problem, there's no friction, no other non-conservative forces that are doing work, I have energy conservation for parts 3, 4, and 5. Part 3 is again where the block is at 1.2 meters above the spring. Step 4, or position 4, is where the block is just contacting the spring. And then position 5 is the bottom of its travel. The spring is at its maximum compression. So I can say that the kinetic energy plus the potential energy in position 3 equals the kinetic energy plus the potential energy in position 4. And I guess the problem didn't ask me for the velocity, but let's go ahead and let's calculate V4. So in position 3, we have 0 kinetic energy because the block is not moving. We do have a gravitational potential energy, mg times H3, and H3 is going to be 1.2 meters, assuming that I put my origin at the equilibrium position of the spring. And the spring has a potential energy of 0 because it is neither stretched nor compressed. In position 4, the block is just sitting above the spring, has not contacted or is just at the point of contacting it. So I have a kinetic energy, a potential energy of 0, a gravitational potential energy of 0, and a potential energy in the spring of 0 because, again, the spring is neither stretched nor compressed in position 4. So the speed of the block just before it contacts the spring is 4.85 meters per second. Again, I want to find the maximum compression of the spring. So I could do energy conservation between positions 3 and 5, or I could do energy conservation between positions 4 and 5. They'll both give you the same answer. I'm going to pick the first one, go from position 3 to position 5. So again, in position 3, I have kinetic energy of 0 and a spring potential energy of 0. In position 5, I have 0 kinetic energy, but I do have a non-zero gravitational potential energy and a non-zero potential energy in the spring, because the spring is compressed in position 5. Now let's take a look at the picture again. So remember that my origin is placed at the equilibrium position of the spring. And that's why in position 3, the height of the block was positive 1.2 meters. So in position 5, the height of the block is going to be a negative d5, whatever d5 is, which is the unknown that I'm looking for. But note that it's negative because it's pointing down, it goes below the origin, so it'll be a negative d5. So d5 is the amount that the spring is compressed. For the potential energy stored in the spring, it doesn't matter whether the spring is stretched out or compressed because this quantity always gets squared. So it'll always be positive. No matter whether the distance is positive or negative, the energy, potential energy, will always be positive. But now notice this is a quadratic equation. If I move everything over to one side, so, as in a lot of quadratic formula problems with quadratic equations, we have two answers. One is negative 0.3 meters, one is positive 0.4 meters. Now, mathematically, both of these solve the problem, but physically, it only makes sense for D to be in the direction that we guessed. The minus sign here means that the direction we assumed D was is actually incorrect. So for the negative 0.3 to be the correct value, that would mean D5, instead of pointing down, actually points up. And we know that physically doesn't happen, that the block does not go up in compressing the spring. So the negative 0.3 is not a physical answer. It doesn't have any physical meaning. So the positive 0.4 meters is the value of D5, which is the compression of the spring. So D5 is 40 centimeters.